Okay, hi guys. Tonight we're going to take a look at residual plots. And residual plot is just a way to compare actual data to the data that we predict. So we've been using the calculator to find the equation for the line of best fit for a set of data, and that equation for the line of best fit gives us predicted data. And residual plots are just another way to see if the line of best fit is a good fit for the data that we're looking at. So residual plot, and that's what we're going to be making today and tomorrow, is a graph that shows the difference between the actual data, the stuff that the data that we put in list 1 and list 2 in our calculator, and the predicted data. And where do we get the predicted data from? The predicted data we get from our line of best fit. The independent variable when we're graphing a residual plot, just like any other graph, is graphed on the horizontal axis, and that's the x-axis, and the residual value, the actual minus the predicted, is graphed on the vertical axis, and that's the y. So when we make a residual plot, we are looking at the residuals. So if the residual data, or the dots, are random and scattered around the horizontal axis, then a linear model is the best fit. If the residual plots or the dots show a pattern, and we'll take a look at those patterns down here, and does not appear to be random and scattered, then a nonlinear model would most likely be a better fit. So let's take a look at these graphs down here. So this is a random pattern, kind of looks like when we were doing correlation, looks like no correlation. This random pattern is what we want to see when we're making a residual plot. And that means that, yes, our line of best fit, our correlation coefficient, all of that information tells us that a linear model or a straight line is the best fit for that data. If we see a U shape or a mountain shape like this, these have patterns, that means that our line of best fit or our linear model is not a good fit. So these two would be, sorry, this one is not a good fit and this one's not a good fit. We're looking for this one right here. Okay, so I know this can be confusing, so let's take a look at some data first. So in this example, the data below shows the number of active woodpecker clusters in the DeSoto National Forest. So this is what we're going to call our actual data. I'm going to write that up here. This is what actually happened when they were looking for the woodpecker clusters in the DeSoto National Forest. The year, so we're going to enter the data in the calculator to find the line of best fit, and X represents the number of years after 1992. So if this is X and this is Y, or this is list 1 and this is list 2, X has to be the number of years after 1992. So for 1992, our X would equal 0. For 1993, our X would equal 1. For 1994, it's 2 years after 1992. X equals 3. 1995 is 3 years. So I'm just doing 1996 minus 1992. That's all I'm doing. And so this is giving us 4. This will be 5. 1998 is X equals 6. 1999 is X equals 7. And the year 2000 is X equals 8. So again, in our calculator, this is going to go in list 1, 0, 1, 2, 3, 4, 5, 6, 7, and 8. And then the active clusters, which is our actual data, is going to go in list 2, 22, 24, 27, and so on. So we entered the data in your calculator to find the last line of best fit. And what did we get for our line of best fit? I'm going to give you a couple minutes to do that. Enter that in list 1 and list 2. Find the line of best fit and the correlation coefficient. We're looking for y equals, and we're looking for our r value, what r equals. So you should have gotten a slope of 3.7 and a y-intercept of 19.867. And then our correlation coefficient was 0.984. This correlation coefficient is very close to 1, so this means that this line of best fit has a strong positive correlation. So we're going to enter this equation right here into y1 on the calculator. So you hit the y equals and then type in 3.7x plus 19.867. So this equation is going to give us our predicted data. So how can we would use this equation to predict the data for active woodpecker clusters after the year 2000. So this one is our predicted data. So when we go to second and graph, it's going to give us an X list and a Y list. The X list, remember, is the years after 1992, so this was X equals 0, X equals 1, and so on. And when we do that on our calculator, in 1992 we estimate there are 20. In 1993 we estimate 24. In 1994 we estimate 27. 95, 96, 97, 98, 99, and the year 2000. And then we can go beyond that. We can see in the year 2001 how many active woodpecker clusters can we expect to see in the DeSoto National Forest. Okay, so what's the residual value? The residual value means we're going to look at the actual data, which is this data right here, and the predicted data that we just figured out using our line of best fit, which is this data right here. I want to know the difference between the actual data, which is 22, and the predicted data, which is 20. So how do we get that information? All we have to do is subtract. So that will give us our residual value. And a residual value is just the actual data that they calculated. They counted 22 active woodpecker clusters. Our line of best fit said there were 20. So our residual value will be 2. In 1993, the actual data was 24. The predicted data was also 24, which is 24 minus 24, and that gives us 0. If I do 1994, it would be 27 minus 27, so our residual value is 0. 1995 is 27 minus 31. That gives us a residual value of negative 4. 1996, it's 34 minus 35. That gives us negative 1. 97 is 40 minus 38. That gives us 2. 98 is 42 minus 42, gives us a residual value of 0. 99, 45 minus 46 gives us a negative 1. And then in the year 2000, it's 51 minus 49, which gives us a residual value of 2000. So we're going to take this data right here, and we're going to make a residual plot. And what that means is we are going to graph the years after 1992, and then we're going to graph the residual value. So keep in mind again that 1992 is the years after 92, so this is x equals 0, x equals 1, 2, 3, 4, 5, 6, 7, and 8. So this residual data, this is going to go on our x-axis, and we're going to plot the residual values on our y-axis, and that's part E. So we're going to construct the residual plot. The horizontal axis will be your independent variable, and the horizontal axis is the years since 1992. And on our vertical axis will be the residual value. So that's what's going to go here, is the residual value. Those are those numbers that we subtracted from the actual minus the predicted. So I'm going to give you a second to set up your scale. We only have to go up to 8. So I am going to cut my line in half, and that will be 4, and then 8 will be here. Cut that in half, that's 2, that's 6, and then in half again will give us the intervals in between. So that's 1, 2, 3, 4, 5, 6, 7, and 8, and of course 0 is right here. On our y-axis, we'll go from 1 to 3 on the positive, so 1, 2, 3. And since we do have negative residuals, we will have to go into the negatives, and so this will be -1, -2, -3, and -4. Now we're going to graph our residual values. So in 1992, when x was equal to 0, that's the years after 1992, our residual value was 2. So 0, 2. At 0 years, our residual value is 2. So we're going to put a dot right there. Let's make a bigger dot so we can see it. Okay, in 1993, when x was equal to 1, our residual value was 0. So this is 1 year after 1992, so this would represent 1993. Our residual was 0. Our residual for 1993 at x equals 1 was also 0. Or 1994, sorry. For x equals 3, our residual was -4. For x equals 4, our residual was -1. For x equals 5, our residual was 2. X equals 6, our residual was 0. X equals 7, our residual was -1. And at 8, our residual was +2. So all we did here was graph, and again, remember this represents the years since 1992. So 0 represents 1992, 93, 1994, 1995, 1996, 1997, 1998, 1999, and the year 2000. And this was our actual data, which was 22 woodpecker clusters in 1992, minus our predicted data, which was 20 woodpecker clusters in 1992. So now we want to take a look at this graph. Is there a pattern? Or is it random and scattered? And so I would say there is no definite pattern, that it is random and scattered. So letter F, would you describe the residual plot as scattered and random? So yes, it would be scattered and random, which means that a linear model is best, meaning our line of best fit works. And that is evident in our R value. Our correlation coefficient was 0.984, and so that's a strong positive correlation. The points, or the residual points or plots, were random and scattered, and that also means a strong linear model. So then we did this correctly. And this is just another way to prove or substantiate or reinforce the fact that that a linear model is best for this set of data. Okay, now it's your turn. Multiple choice question number 1. Looking at the graphs below, decide what the line of best fit would be. So you're asking yourself, are these random or scattered? Or does it have a pattern? If it's random and scattered, it would be a linear model. If it has a pattern, it would be nonlinear. Or maybe there's not enough information. Or maybe it's both linear and nonlinear. And then looking at number 1, how did you decide what the line of best fit would be? Describe the relationship pattern between the data. So what you're describing is, what does the residual plot look like? So you're not writing an equation, just tell me, what does this residual plot look like, and does it give you a linear or a nonlinear model? Please make sure you answer your questions in the Google form.